students, now we are going for the next topic, that is your in 11.5 we are having Ohm's law. Already we have learned in the lower standard. Again we will repeat this. We are having in Ohm's law the relationship between, that is given by a scientist, physics scientist, George Simon. It is a relation between current flowing inside the conductor and potential difference applied across the ends of the conductor. Like we know, if we are having a conductor, again if I am telling the same thing, if we are having a conductor, a copper rod, a metal, electrons are flowing. So when an electric field is applied, we know electrons flow from a lower potential to higher potential. Now here I am just making, this is an atom which is there. Large number of atoms are present inside the metals, that is copper rod, and if a potential difference is applied across this, an electric field is applied across this, electron starts moving from lower potential to higher potential, hence a conventional current flows from higher potential to lower potential, that is from positive terminal to negative terminal. So it is a relationship between the current and the voltage. What Ohm's law tells you? For a given physical conductor, if the state of the physical conductor remains the same, the current flowing inside the conductor is directly proportional to the potential difference applied across the ends of the conductor. It means the Ohm's law tells you the relationship between the current flowing inside the conductor, that is due to electrons, and the potential difference applied across the ends of the conductor. So potential difference is basically that is due to the battery or due to cell. So potential difference. So more is the potential difference. More is the potential difference applied across the ends of the conductor, more will be the current flowing inside the conductor. We can add I proportional to V, as long as the physical state of the conductor remains the same. So that is in the lower standard we have seen, as long as the physical state of the conductor remains the same. Physical state means its length, we are having its area of cross section. Okay, the temperature we can tell. As long as the physical state of the conductor remains the same, the current flowing inside the conductor is directly proportional to the potential difference applied across the ends of the conductor. I proportional to V, or we can write V proportional to I. See, sometimes what happens is basically we can write V proportional to I also, and here also sometimes we write I is equal to constant, proportional goes, it is equal to K times V, or we write here in textbook it is given C times V. C is constant. Okay, or we write this is 1 upon C, so here it becomes 1 upon C times V. So this 1 upon C is nothing, this where C is called conductance. Okay, so where C is called conductance, and 1 upon C is basically it is the reciprocal of resistance. You will see what is resistance. Okay, in the textbook it is given I proportional to V or V proportional to I, and therefore we can write V is equal to I into R. So V I proportional to V or V proportional to I here, and the potential difference is equal to current into resistance, where R is the resistance of the conductor. So here we can tell that R is the resistance of the conductor, which is the ratio of potential difference applied across the ends of the conductor to the current flowing in the conductor. R is a constant. So here where R is the resistance of the conductor. Where R is the resistance of the conductor. So it is constant for a given conductor. It is the ratio of applied potential difference to the current. R is constant. Moreover, we can define one more term called as conductor. So resistance is basically it depends upon the conductor itself. Okay, but more is the voltage, more is the current. That is Ohm's law. Relation of Ohm's law is more is the voltage, more is the electric field due to battery, more is the electric field, more is the voltage. If more is the voltage applied across the ends of the conductor, more will be the current flowing inside the conductor, and resistance will remain constant. The resistance of the conductor remains always constant. Any conductor we take, the resistance of that conductor remains constant. Suppose copper it is, then the resistance of that remains constant. Suppose it is a silver, its resistance is constant. But more is the voltage, more is the current flowing. So that what is your Ohm's law. Next is we should know here again they are defining one term called as a conductance. In the textbook, conductance is nothing, it is a reciprocal of resistance. It can be written as C is 1 by R, or sometimes you can write it as K also. Okay, here we can write unit of resistance. We are having what is unit of resistance? Everyone knows unit of resistance is your ohm, OHM, ohm. Symbol for resistance is this, ohm. Okay, and conductance is C is 1 upon R. So unit is just reciprocal of this resistance. We are having ohm here. We can write the reciprocal of resistance is mho, and we can just put the sign like this. This is mho, the unit of conductance. It is the reciprocal of resistance. Okay, resistance, unit of resistance is ohm, that is this symbol, and unit of conductance is mho. It is the reciprocal of resistance. So here one more thing we should know about a graph. Suppose here if we are going to talk about the graphical representation of IV characteristics, or V across I. In textbook now it is given V across I, sometimes they give I across V. More is the voltage, more is the current. So whatever graph you should get, expectation of the graph is something like it should be a straight line. Okay, it should be a straight line. Now this is your basically ideal graph. Ideally, when it is ideally, it should give a straight line. So more is the voltage, more is the current. 1 ampere, 1 volt, 1 ampere, 2 volt, 2 ampere. So it is the ratio will be, so ratio is going to remain constant. So you are going to get a constant ratio. Okay, but what actually happens, that is due to heat. We should know, due to heat, now due to the collision of the electrons, we will study further. Due to the collision of the electrons in their way, the heat produced here due to the collision of electrons with an atom on their way, and due to the heat, the atom starts vibrating very vigorously, and there will be more chances of colliding of electrons, and hence it is going to produce more resistance. We will see later on. But the graph here, the practical graph, if you are going to see, it is not exactly straight line. If you will see, it will go something like this initially, and as the temperature goes on increasing due to the collision, this is what practically you are going to get something. Instead of exactly a straight line, you can get this practically. So practically the graph is not exactly a straight line. So this is practically we are going to get. Okay, and we are having ideally is this, that ideally we are just drawing a straight line. So basically ideally we should get this one, but practically it is this. Moreover, we know what is your resistance. R is V upon I. The unit of resistance is ohm, unit of potential difference applied is volt, and unit of current is ampere. So we can tell 1 ohm is 1 volt upon 1 ampere. It means when a potential difference of 1 volt is applied across the ends of the conductor, that is 1 volt ka battery if you are applying across the ends of the conductor, and which will cause a current of 1 ampere to flow through it. We can measure ampere, we can measure current with the help of ammeter, we can measure voltage with the help of a device called as voltmeter. So when a potential difference of 1 volt is applied across the ends of the conductor, which will cause a current of 1 ampere to flow through it, then the resistance of that conductor, whatever the conductor is, suppose you are having copper wire, the resistance of the conductor is said to be 1 ohm. So unit of resistance is 1 ohm. So what is the meaning of 1 ohm ka resistance? 1 ohm ka resistance of a conductor is when you are applying a battery of 1 volt, which will cause a current of 1 ampere to flow through it. Let us go for now physical origin of Ohm's law. Physical origin of Ohm's law. What we are going to study in this? We are basically going to study about the relationship between current density, electric field, torque, the tau, average, time between two successive collision, average time between two successive collision. So let us begin with the topic. We are seeing some relationship between here and Ohm's law. What basically happens in the Ohm's law is, again, if we are going to take a conductor, inside a conductor there is large number of electrons, which is due to electric field. When electric field is applied across the ends of the conductor, electron starts moving in a particular direction. With a drift velocity. Same thing, we are having large number of atoms which is there, and we are having all these electrons are conduction electrons, which have been delocalized. Atoms are there, and we are having large number of electrons which have been delocalized, and initially they was moving in all possible direction. So inside the conductor, the net when the electric field is not applied, the delocalized electrons, they move in all possible direction. We have seen before, and when an electric field is applied, the electron drift and start moving with the same speed, that is with the drift speed. We have seen what was the drift speed, very low, 10 raised to minus 4 to 10 raised to minus 5 meter per second. They all starts moving with the same velocity from lower potential to higher potential. When they move from lower potential to higher potential, they start colliding. They start colliding with the walls of the container and with the atoms which are present in their way. Before this, when electric field is not applied, the electron was not colliding with other electrons, but it is assumed that electrons are colliding with the atoms, and again they are randomly moving in all possible directions. Same thing when the electric field is applied, the electrons collide with the atoms and the walls of the container. They will not collide with other electrons, but they are going to collide with the atoms present in the way when they are moving from lower potential to higher potential, that is from one negative terminal to positive terminal. Now when they collide, the drift velocity is not going to change instantly. When we take at any instant time, the drift velocity will not change. They will collide, they will just move randomly, and again due to the applied electric field, they will start moving continuously in the same direction, that is from lower potential to higher potential. So the drift velocity will not change. So here we can just take that due to the electric field, the force applied on the electric field F is, we know F is Q into E. Force acting on a charge is due to the electric field, due to this battery, due to the electric field, which is pulling the electrons. The electric field is from positive to negative, so it is applying with the electric field, it is pulling the electrons from negative to positive. So due to the electric field, force acting on the charge, that is F is equal to E instead of Q, E. This minus sign, if you are going to put it, is, you should know it is an electron. What is we are having? F is equal to ME is EE. Okay, and then therefore again we can write A is acceleration will be acting on the electrons due to the electric field. So they will be accelerate, constant acceleration will be there, constant due to constant electric field force is there. So acceleration will be there, that is EE upon M. So acceleration will be there due to the electric field, that is AEE by M. Now we should know, so whenever the electrons are moving, they are having an acceleration, they are colliding with the atoms in their way and the walls of the container. So the time taken, so let we write that let tau is called as let tau. These are the symbol of tau, let tau be the time taken or average time taken between two successive collision, So between any two collisions, the time taken is tau. So let tau be the time taken between two successive collisions. So they will collide and again they will start moving in the same direction. Again they will collide, again they will start moving with the same direction. So the velocity, the drift velocity here it is given by, therefore we are having v which is equal to here a tau. We write a tau. So basically v equal to u plus at. You should know v is equal to u plus at. V is the velocity, that is final velocity at any instant time t. Velocity is given by u plus at. U is 0, initial velocity is 0, and then acceleration is there, and tau is the time taken. So instead of v equal to u plus at, we are having v equal to u is 0, then plus at will be there. So we are having v equal to at, and then we are having v which is equal to a. Acceleration we take from here, this equation. From this equation we write your acceleration is E upon m into torque. Okay, so E is charge of electron, electric field, mass. We are having that is tau, time taken between two successive collision. Moreover, we are having your also we know what is the relation between your current density and drift velocity. That is Vd. We can just write here, if you won't write, we can write Vd, drift velocity, J upon any. J is any Vd is J upon any. Initially we have proved, and therefore we can also write it is E upon m. We write it as tau is J upon any. So relation between, so your E is, therefore we are having E is equal to, we write it is, here it is J upon, here it goes N E square, E comes down, this tau is going to come down, okay, and we are having, so we are having here M will go here, and then we are having, this is all constant, we will get it as J, that is current density. Here we are having E is, M will go here, M upon NE square, tau comes here J. So this is the relation between your electric field, your battery you are applying, and current density. More is the electric field, more is the current flowing fluid, current density is more. So here we take, therefore we write E is rho into J. Now here in new term we are having here rho J, where rho is constant called resistivity of conductor. Okay, rho, and rho is equal to N. Rho is equal to, what is rho? It is m constant, it is N E square, this is tau. This is again rho is equal to M E square tau. It means here we have seen the relation between electric field, current density and resistivity. Here rho is resistivity is constant called resistivity of conductor, because resistivity here it is now depending upon m is mass of the electron, n is number of electrons which is there flowing per volume, E is the charge of an electron, and tau is the time taken between successive collision. It depends upon how the conductor is, how much will be the time taken between two successive collisions. So different conductors we are having different tau, but for this particular conductor we are having here, suppose copper wire, the tau is constant, mass of the electron is constant, charge of the electron is constant, number of electrons per volume is constant. So you finally E and J, more is the electric field battery which is applied, more is the current density, and then E is rho. Rho is the resistivity, that is again becoming constant due to the resistivity of a conductor for a particular conductor, and here rho equal to M upon N E square tau. So rho will here, rho is independent of electric field because rho depends upon mass of an electron, number of electrons per volume, charge of an electron, and tau, that is time taken between successive collision. So basically resistivity will not depend upon your electric field, but current density will depend upon your electric field. Students, now let us go for limitations of Ohm's law. What we can discuss here is, we are having a graph of, I've already drawn the graph of Ohm's law, but Ohm's law, basically the graph is a straight line. Here we are having, suppose, some characteristics like I and V, or we can add V and I, but here we are just going I and V as in the textbook. We can have something like, suppose this is something like this. Now this is behaving some differently instead of a straight line. Now this graph is for non-ohmic conductors, non-ohmic substance, non-ohmic conductors. Okay, so this is a type of a graph. Limitation of Ohm's law, basically Ohm's law is limited to only for conductors like metal, like copper, we are having silver. There the Ohm's law is obeyed. The graph we have seen before was a straight line passing through the origin, V versus I, or here I versus V. So there is a limitation of Ohm's law in different material, like we are having materials such as vacuum tubes, semiconductors, devices, diodes, thermistors. We have seen thermistors, we have seen in an iron, that is inside soldering wire. We can see thermistors, we can see in EPCs, then we have seen diodes. What happens basically here, when we are increasing the voltage, so current should increase according to Ohm's law, but at particular voltage, or at when voltage is suddenly increase, when voltage is slightly increased, what happens, there will be large flow of current. So that basically happens in case of diodes, in case of vacuum tubes, in case of thermistor. So it will not obey the graph straight line, it is not going to obey Ohm's law. So the graph for non-ohmic conductors which doesn't obey Ohm's law is, suppose, this type of graph we are having here. So what is the limitation of Ohm's law? Ohm's law cannot be applied to all material. It can be applied only for good conductors like copper. It cannot be applied for thermistors, diodes, we are having vacuum tubes. Okay, so here we can just see the formula for resistance is basically R, which is equal to V by I. But if we are going to see limit of delta I tends to 0, there will be, for a small change in voltage, there can be large change in current, and or vice versa. For a very large change in the potential difference, there can be very small change in the current according to different types of material. So R, we are putting a limit here, R equal to, instead of V by I for Ohm's law, we are writing R equal to, for non-ohmic conductors, we are writing resistance R is limit delta I tends to 0. Very small change in current, delta V by delta is, that can be written as dV by di. Moreover, if we can take two values, for two values of potential difference, for two values of potential difference, two values of potential difference, we can write V plus delta V by 2 to V minus delta V by 2. In a graph, we can take any two values for the potential difference, and the current V, for two values of V plus delta V upon 2 to V minus delta V upon 2, the current will be, the current delta I can be noted, and generally we write R is dV by di, that is change in the voltage, dV, V plus delta V by 2 to, suppose V minus delta V by 2. we can note down the current delta I can be noted with the help of this graph. That is for non-moving conductors. Next topic, students, we are going to learn about electrical energy and power. Electrical energy and power. Relation between electrical energy and power. Already we are knowing the lower side, we have seen energy is nothing, it is a work. Power is the rate at which work is done, or the rate at which energy is supplied. Here electrical energy and power, we'll just see, suppose let us take a small resistor. It can be a bulb, it can be rechargeable battery, it is a resistor which gives resistance, small device, a resistor, and if you are going to apply a potential difference, what is going to happen? The current is going to flow. If you apply potential difference, current starts flowing through the resistor, and the resistor is going to, this resistor can be a device, so current flows and then the resistor starts working. What we basically want to know here is, when we are applying the potential difference with the help of the battery or with the help of the cell, we are providing potential difference across the resistor, that is higher potential to the resistor like a bulb or like a fan or like a rechargeable battery at one end, and lower potential to the other end. So here we write the potential difference applied across the resistor is the work done in moving a charge. The work done in moving a charge. So when a potential difference is applied, the work is done in moving a charge, so that the charges is going to move inside the resistor from higher potential to lower potential. Means the energy is supplied to the charge. Basically, with the help of this battery, we are supplying the energy. We are supplying the energy to the charge, and then the charge goes, and that charge, when it is inside the resistor, it will supply the energy inside this, so that this device is going to start, it is going to work, and hence it is going to lose the energy on moving from, is going to lose the energy from higher potential to lower potential. So V is the potential difference applied. The potential difference applied is 2, so that the work is done in moving a charge from higher potential to lower potential. V is W by Q. Or we can just write it is W is equal to Q into V. Here, what is Q? It is, Q is IT. We write current into delta T, that is into V. So it is, Q is nothing, it is I into T, and this work done is nothing, it is given by change in the potential energy. So when we are giving energy with the help of battery to the charge goes and it gives the energy to the iron core inside these ions, inside this, and this device starts working like a bulb. So when it gives the, when the electrons are moving, when the charge are moving, it collides with the iron core inside this device, and then it starts working. It means there is a loss of energy. So there is a change in the potential energy, that is from higher potential energy to lower potential energy. So there is a change in the potential energy. So that is the work done. Work done means basically nothing, it is the potential energy. There is a change in the potential energy. So here, when you write delta U upon delta T time, that is IV, and when we put limit to this, limit of delta T tends to 0 in a very small time, delta T tends to 0, this becomes dV by dt, or we can write du upon dt, change the potential energy. is IV. It is nothing, change in the potential energy is the rate of change of energy, that is nothing, it is power. Power is IV, or we can add power is voltage into current. So relation between electrical energy and power. So basically we are giving, from the battery we are giving power to the resistor. That is when we are giving power to the resistor, that is the device, rechargeable battery or bulb, it glows. So it is a work in moving a charge. From the battery, from the cell, we are giving energy, we are giving power, we are giving energy to the charge. It moves, and inside the device it collides with the ions. It collides with the ions, and then energy, it collides with the ions, and when it collides with the ions, the electron, when it collides with the ions, the heat is produced. Energy is dissipated while moving from A to B. So the power is given by, power given to the charge is also given by, power is voltage into current, that is V by I. Moreover, according to Ohm's law, also we know V is equal to IR. So this power dissipated, or power is voltage, that is instead of V we can write IR into I. When we substitute, we can get I square R. And also we can write I is V upon R, that is V square by R. When we substitute here, V is V instead of I, we can add V by R from this, and we can get V square by R. So we can get V square. So we can get the formula for power is I square R, V square upon R, and we are knowing power is nothing, just voltage into current. So this is the relation between electrical energy and